Hi, my name is Corey. I'm part of Group 4 for the final project along with Brendan and Cordell. And today we're going to be covering flow simulation, a little internal and external flow, just some examples. So first we're going to be covering external flow, and for that we chose the spoiler. So you're going to want to get whatever part you're doing loaded up, and then go to flow simulation. If you don't have that tab, you can right click anywhere up here, go to tabs and add it here at the bottom. Next, you want to click on Wizard to set it up and name it something appropriate like external flow. And I'm just going to leave it in SI units, and these parameters all look good, so I'm going to hit next. Now we're dealing with external flow, so I'm going to switch that over and check both of these boxes. What these boxes do, checking them, this will prevent SolidWorks from filling the wing body with fluid. And then the only thing that matters here is the gravity. So it's got negative 9.81 in the Z direction, or in the Z component, but as you can see, our coordinate system down here, we're going to need it in the Y direction, or negative Y direction rather. So change that to 0 and move that up here. Hit next. For gases, we're dealing with air, obviously, as it's spoiler on a car moving through the air. So you click that and hit add, and you see it shows up right here. You can choose laminar or turbulent or both, and we're just going to leave it here at both, which is the default. We're not going to worry about wall conditions, so just hit next. And then the only parameter that we're going to be changing here is velocity in the Z direction, which we're going to set it to negative 80 for our case. That's about 180 miles per hour, and it's the average track speed of a Formula 1 car. So then hit finish. Zoom out a little bit. Let's see. So this box is called the computational domain. This is where the calculation is going to be run for. And we're just going to go ahead and extend this back wall a little bit, just so we get more calculation, and we might see a little more stuff what's going on back here by extending it. And then the last thing to do before you actually see your results is add some goals. So we're going to click on global goals, and you can pick any of these as it pertains to your situation, but we are going to stick with force in Z, force in Y, and the normal force also in Z and Y. And hit OK. And then you hit run, and it's a new calculation. Click run, and you should see another window popping up. There it is. So this is going to prepare the model and start running iterations to solve until it can find a solution and converge. And this is going to take a couple of minutes, but after that's done, you can get into the post-processing, which is where I'll send you to Brendan.
Okay, now let's do some post-processing. For starters, we're interested in our coefficient of drag to find this equation here. So I'm going to create a new goal as an equation goal. I'm going to input some of these quantities. First, we're going to use our force in the Z direction, which is our drag force. And another thing we need is velocity in the Z direction. I'm going to insert that as a parameter, just like this. Double click, and we have it right there. Now the other quantities of interest to us we had to input into that equation were our density of the fluid and our area normal to the direction of flow. So let's say I forgot my density of air. I could come in here and go materials, gases, air, and right here I have these quantities and these quantities. So that's kind of useful. Now for my area normal to the direction of flow, I just copied my part, used silhouette entities, evaluate section properties, and I grabbed that value right there. So now we've specified that we want our simulation to run until all these goals have in fact converged. Let's see what they converge to. I'm going to go insert under goal plots. I'm going to choose my coefficient of drag that I defined. I'm going to hit show, and I can see the value it converged to. I can see that it was used in convergence, and it shows up as newtons, but I just specified the output value wrong, or rather the output units wrong. It should be dimensionless. I can show a plot of it, and I can see here that it did in fact converge as our iterations progressed. So I'm going to hide this guy, and now let's look at some of the plots we can create. We're going to start with flow trajectories. These are a great way of visualizing different types of fields. So I'm going to make a velocity field on the right plane. I'm going to select the right plane. I'm going to select velocity as a magnitude, and I can hit show to view a preview of it. I can then change things like from arrows to spheres, the size of them, the spacing of them, and I can also choose between a static or a dynamic trajectory. So I've already created a few here, and if I hit play here, this is a dynamic trajectory. You can see it's moving. You can see I defined 3 different planes I wanted to view this on, and you can see our low velocity and high velocity regions. So now let's go ahead and look at this static velocity trajectory I created. And so here, since it's static, we're just going to view it forming rather than a consistent motion. And this is useful for visualizing flow separation. So let's go ahead and hit hide here. And let's look at a cut plot. So let's start with a velocity streamline cut plot. I'm going to hit play, and it's going to move throughout this range of cut planes I've specified. And we're going to see these vortices forming as well as these low pressure regions forming. So now we can look at a pressure contour map. And here we can see we have low pressure on the bottom and high pressure on top, consistent with the downforce we're trying to create. We can go ahead and hit hide or show these maximum values, and they'll show up here. And say we want to adjust our color map a little bit. So we can come in here and we can say I instead want this to be grayscale. I can hit show to update it. Now we have it in grayscale. I can also come in here and say I want to use less or more values to make this coarser or denser. Another way that we can visualize our pressure differential is by going in surface plots. I selected this top surface as well as this bottom surface. We can see again, consistent with our legend, we have higher pressure on top, lower pressure on bottom. And let's say our behavior here was not quite what we expected it to be, and we have to rerun our simulation. I can show my mesh overlaid on this, and that'll give me a better idea of where I might want to actually refine my mesh when I rerun my simulation. So now let's look at some ISO surfaces. I'm going to hit show here, and I'm going to edit it, and this is just a great way of showing a representation of the fluid medium that is in this pressure region. It doesn't have to be pressure, I can choose anything, but I can also add a second value. I can update it, and now we have this higher pressure shown up here and the lower pressure here. I can move this around a little bit and see how my representation changes. So I'm going to hide that, and now let's say we want to export some of this information in a useful manner. One way of doing that is an XY plot. So here I've plotted my pressure against each of these 3 edges, and I can export that to Excel or save it as an image for use in a memo. Now another thing I can do here is go into report, and I can export all of this all at once by going from template, and I'm going to choose flow sim report. I've already done this. And this is what it's going to output. It's going to be just a concise summary of all of the inputs, outputs, and an appendices of where it grabbed different values used in the simulation. And one other thing we can do is create an animation. And this is not a super useful animation. The purpose is just to show that you can do it. So thanks. These are a few ways you can do post-processing in SolidWorks Flow.
Another cool simulation that we can set up in SolidWorks is an internal flow simulation. So let's say we have this tank here, and we're filling it with liquid nitrogen and liquid oxygen coming in through these bottom inlets, and then they're mixing in this tank and then leaving. And we're going to set this up as a transient simulation, so we're going to be looking at the solution as time changes, because we're initially going to fill this entire tank with liquid nitrogen. So we're first going to come up to the wizard. We're going to say this is the mixing tank. Click next. We're going to select SI units. We're going to leave this as an internal flow simulation. For this simulation, it doesn't really matter. You can check this or not check it. Doesn't really matter in this case. But we are going to be doing a time-dependent study. So this is the transient part of the simulation. So we're going to run this for 30 seconds, and we're going to output solutions every 0.1 seconds. Then we're also going to include gravity in the simulation. So this is going to be in the negative x direction. We're going to click next. Then we're going to add our liquids. So again, we're going to come down to liquid oxygen, click add, and nitrogen. And then we're going to leave this as laminar and turbulent, since we can have either types of flow in the simulation. Click next. We're going to set this to 15 micrometers for the roughness, which is a typical roughness for, say, like stainless steel pipes in an industrial application. And then this is our initial condition screen. So we're going to leave the initial velocity of our fluids at 0. All that's good, temperature's good, but we do want to change this to have our entire fluid model filled with nitrogen at the very beginning. So then we're going to click finish, and then it's going to SolidWorks is going to freak out and say this model is not watertight. We want to have a watertight model for internal flow simulations. So it's going to ask, do you want to open the lid tool? We're going to say yeah. And we're going to come down and we're going to click on these faces where we have openings in our model. And SolidWorks is going to automatically cap these openings using the lid tool. So we're going to create those lids. So now our model is fully sealed. We're going to say yes to that, yes to that. And then we're going to insert our boundary conditions on that interface of those lids. So then this is going to be our inlet for our nitrogen. And then we're going to say substance concentrations. We want it to be fully nitrogen, which it already is. Click check. And then we're going to insert boundary conditions on the inside of this lid as well. We're going to pump in the same amount, same mass flow rate, but this is going to be all oxygen. Click check. And then for our outlet, we're going to have an environmental pressure outlet here. Environmental pressure. There we go. And then our simulation is set up. Another thing that we want to come and do is click on calculation control options and go to saving, periodic, and then we want to come in here. Since we're wanting to look at the mass fractions through time, we want it to save this information in this simulation. So we're going to click OK, and then we're going to click Run. Solve new calculation, and SolidWorks is just going to run the iterations on this fluid model. It's going to pop open our solver window, and when it's done, we can perform the post-processing on this. So after our solver has finished doing the iterations on our model, we can go ahead and take a look at the results and start doing the post-processing. Right now I currently have set up all the plots in here, but basically if you want to insert any of these plots or flow trajectories, you just right click on them and then click insert, and it will take you through what you want to plot on any of those surfaces, where you want your flow trajectories to start, and then a couple different options. But for now, let's take a look at the plots and flow trajectories that I have set up already. Right here we have a cut plot. So a cut plot, we can plot information on a plane that cuts through our model. So right now I have this plotting the volume fraction of nitrogen in the tank, and then this is displaying this at the end of the 30 seconds. If we want to go through and see how that changes through time, we can open up this Transient Explorer option and then take it back to the beginning of the model. So how we set up our model, if you remember, our initial conditions was that the tank was entirely filled with nitrogen, and then we were pumping them in both through these inlets at the same mass flow rate, so we can see how the volume fraction changes through time on this cut plot here. So that's pretty cool. For now, we'll exit the Transient Explorer. Other things that we can do, we'll hide that. We can do a surface plot, so we can plot the volume fraction of nitrogen leaving through this outlet on the surface of our lid. And if this probe feature, right now I have the probe on, but the probe is right here, so you can select that. So you can actually read results, select points off of your plots and see the values there. So that's the surface plot. We can also go, I'll hide that. We can show isosurfaces. Isosurfaces create a surface given a certain parameter. So right now, this surface is created everywhere where the volume fraction is equal. And then we can go ahead and plot another parameter on that surface. So now I'm plotting the velocity on that surface everywhere where the volume fraction is equal. Another cool thing is the flow trajectories. So we can show all these flow trajectories, and we can actually go ahead and play our flow trajectories as well. This is useful for seeing areas of recirculating regions in here. So we see that we get some recirculating regions in the bottom here, as well as at the top of the tank, and it's being driven by these inlet flows. So we can hide that. If we want more quantitative results, we can go to the XY plot, and we can show this. So right now what this is doing is it is taking the results and plotting the volume fraction of nitrogen along this line. And so we can see at the end of the 30 seconds the distribution of the volume fraction on this line. So basically this line is acting like a probe throughout the tank. And we can also, if we open up Transient Explorer again, we can take a look at this plot at the beginning of time and then see how it changes as time progresses. So yeah, that's how to set up an internal flow simulation in SolidWorks with some mixing species concentration and do the post-processing on the results.